Welcome back to the deep dive. Grab a comfortable chair, maybe a cup of tea,
Yeah.
because today we are diving into something absolutely wild.
Mm-hmm.
We're talking about a ghost ship from a forgotten era of the universe, a piece of ice moving so fast it really shouldn't even exist. We are talking about 3I Atlas.
This is truly a cosmic vagabond. It's the third confirmed interstellar visitor we've ever had passing through our solar system, and honestly, probably the weirdest one yet.
The weirdest how.
Dynamically, chemically, historically, you name it. We're going to unpack why this object, 3I Atlas, has scientists scrambling and why, for a few hectic months, half the astronomy world was wondering if it was an ancient alien artifact.
Right, performing a secret solar-breaking maneuver.
Exactly.
That 3I stands for the third confirmed interstellar visitor, following the slightly weird cigar that was Oumuamua and the slightly more conventional comet Borisov.
Right.
This new traveler was first clocked back on July 1st, 2025 by the ATLA system, which sounds very mythological, but it's actually a fantastic system called the Asteroid Terrestrial Impact Last Alert System.
It's our high-tech eye in the sky.
Yeah.
And the most important defining characteristic of 3I Atlas is that it's flying on an unbound path. It's on what astronomers call a hyperbolic trajectory.
Hyperbolic, so fancy word for it is not coming back.
It's a one-way ticket. It came in, got a gravitational nudge from the sun, and it is absolutely gone. Its official designation is C2025N1, ATLAS, and its journey through our neighborhood is a one-time thing.
Okay, so let's really unpack this, because when we say this thing is wild, we mean it hits every marker. Extreme velocity, chemistry that just defies our local expectations, and yes, that high-profile scientific speculation about alien technology. We're going to dive into why its weirdly high carbon dioxide content suggests it might be the oldest comet ever seen, where this ludicrous speed actually comes from, and why we had to deploy the biggest radio telescopes on Earth to prove it was, just a natural object and not some kind of stealth probe.
It's a stellar example of how the natural, chaotic universe can often deliver stories far more compelling than our most creative science fiction. But you have to respect the initial buzz.
Oh, for sure.
The simple facts about its speed and age were enough to cause chaos. So let's start there, because its velocity is genuinely unprecedented.
It's not just fast, it's a record breaker among our interstellar visitors.
Yeah.
When 3I Atlas first came ripping into the inner solar system, it was screaming along at about 61 kilometers per second relative to the sun.
Which is roughly 140,000 miles per hour.
Oh, insane.
That initial speed is called the hyperbolic excess velocity, and it's the velocity the object maintains far away from our sun's influence. To put that 61 kilometers into perspective, look at the previous two. Oumuamua, the first one, was moving at a clip of about 26 kilometers per second. Borisov, the second one, hit about 32 kilometers per second.
Hold up. So this comet nearly doubles the speed of the next fastest interstellar visitor we've seen. That is absolutely bananas. Is there like a speed limit for these things?
Not really, but that comparison just shows how unusual 3I Atlas is. It is an absolute unit loaded with galactic momentum.
Right.
And when it hit its closest point to the sun, its perihelion, on October 29, 2025, it peaked at 68 kilometers per second. That velocity is so high that the sun's gravity simply couldn't bind it, not even slightly.
We're used to things in space moving in ellipses, nice little loops, but this thing is just cutting across the cosmic parking lot.
Exactly. Its trajectory is defined by an extreme orbital eccentricity of over 6.139.
6.139. Okay, so for anyone tuning in who hasn't reviewed their Kepler orbital mechanics since college, an eccentricity of 1.0 is a parabola, right?
Right. That means the object just barely manages to escape gravity.
And everything we know in the solar system is less than 1.0. They're all bound orbits. But 6, what does 6 even mean in physical terms?
6 means its path through our solar system looked almost straight. It didn't really curve around the sun so much as it just whipped past, taking a single gravitational slingshot, and kept on going.
Wow.
This is an incredible amount of kinetic energy. I mean, to give you a relatable analogy, the fastest human-made objects, like the Parker Solar Probe, which uses the sun's gravity assist, that maxes out around 190 kilometers at perihelion. But Parker's doing that because of massive thrust and gravity assists from planets.
Right, it's cheating.
It's cheating. 3I Atlas is doing 61 kilometers before the sun even assists it. That velocity relative to the local interstellar medium is why it's so much faster than its predecessors. This comet has serious galactic momentum accumulated over billions of years.
But this speed isn't just random noise, though. If it's moving that fast, What does that tell us about where it came from? This is where it gets really interesting because it connects to, like, galactic archaeology.
Yes. Astronomers traced its origin dynamically, looking not just at its blazing speed, but crucially at its angle of approach.
Oh.
They analyzed its proper motion relative to the sun and the rest of the galaxy.
And what did that motion vector point to?
Well, they analyzed its high vertical velocity component. That's its speed perpendicular to the galactic plane, the flat disk where most of the stars, including our sun, orbit.
Right, the frisbee part of the galaxy.
Exactly. And they connected that high vertical speed to the Milky Way's thick disk population.
Thick disk. Okay, so we hear about the thin disk, that's where our solar system lives, the spiral arms, the young, metal-rich stars.
Hmm.
What defines the thick disk, and why does its vertical velocity matter so much?
The thick disk is the older, puffier, and much less organized part of the galaxy. Stars here tend to orbit at steeper angles, bobbing up and down more vigorously above and below the thin disk.
It's more chaotic.
Much more. It formed early in the galaxy's history, likely through violent mergers with smaller satellite galaxies. So the stars in the thick disk are generally metal-poor, meaning they have fewer heavy elements than our sun because they formed when the universe was younger.
So 3I Atlas is moving so fast vertically that it suggests it originated from a population of stars that is inherently wobbly, the thick disk.
Exactly. This high vertical velocity is the dynamic signature of a very old population. And the implication is, well, it's profound. It's bordering on unbelievable.
What's the implication?
If 3I Atlas originated from a star system born in that thick disk, researchers estimate it could be between 7 and 14 billion years old.
Wait, 7 to 14 billion.
Billion with a B.
Our solar system, our entire planetary neighborhood, all the rocks and ice we've ever sampled is what, about 4.6 billion years old?
That's right.
So we might be looking at a piece of cosmic heritage that predates the sun by billions of years. That's just a staggering thought.
It is. I mean, imagine this piece of primordial ice and rock, frozen solid, wandering the galaxy for longer than Earth has even existed. It survived the early, tumultuous period of galactic history. It's an object from another era of the galaxy.
Whoa.
That level of antiquity gives us, essentially, a time capsule, a glimpse into star systems that formed billions of years ago when the chemical makeup of the galaxy was fundamentally different.
Man, that's the kind of fact that makes you feel connected to everything. That's a serious aha moment. So it's ancient, it's fast, and we almost missed it because of where it was coming from, right?
That's another layer of complexity here. The discovery happened on July 1st, 2025, thanks to the ATLA system in Chile. But earlier pre-discovery observations showed it was active way back on May 7, 2025.
And it was super far away then.
It was 6.4 AU away. That's far beyond Jupiter's orbit.
6 AU out, and it's already active. We'll get to the chemistry in a moment, but why was it so hard to spot initially?
Because it originated from the southern celestial hemisphere, coming in almost directly from the direction of the galactic center in the constellation Sagittarius.
Ah, so the busiest, most cluttered part of our view.
Precisely. Trying to spot a faint, fuzzy object like a comet against that bright, dense, glittering background is incredibly challenging. It's like trying to spot a piece of coal moving across a black felt sheet covered entirely in tiny diamonds.
So they had to use some fancy tricks to even see it.
They had to use very precise astrometric solutions and deep difference imaging, basically subtracting images taken over time just to pull the faint moving object out of that immense background noise.
Wow.
This necessity explains why its discovery was relatively late, despite its enormous activity.
And thank goodness for the diligence of the survey teams, because what they found about its composition and activity is arguably the strangest part of this whole story. We're talking about a comet that spits rocks at the sun and is inexplicably fizzy.
Yeah, it's less a typical chunk of dirty ice and more a space soda that's been shaken up for 10 billion years.
What do you think? Comment below. Do you find the idea of an object being twice as old as our sun more compelling than the idea of an alien probe? Does that antiquity make it feel more important? Let us know.
So when we talk about cometary activity, we're witnessing the sun's heat sublimating the ice off the nucleus, creating the coma, that fuzzy gas and dust cloud, and eventually the tail.
And 3I Atlas exhibited unusual behavior right out of the gate, didn't it?
It did. It suggested its interior is fundamentally different from solar system comets.
The early observations, back in July 2025, were already seeing massive activity. It had a slightly elliptical coma that was enormous, roughly twice the diameter of Earth, spanning tens of thousands of kilometers.
And initially there was this strange color profile. When first observed, the dust exhibited a reddish color.
Like 2I Borisov, the other interstellar comet.
Exactly, and similar to very dark, ancient D-type asteroids. That reddish hue is generally attributed to Tholen's irradiated organic compounds, basically space sludge built up over eons of cosmic ray exposure.
Ah, the classic space dirt crust.
Right. But here's the interesting dynamic. Early on, the coma featured an unexpected sun-facing plume. It appeared elongated toward the sun, not away from it.
Wait, a plume facing the light source?
Yeah.
That seems fundamentally backwards. We expect tails to trail behind, pushed by the sun.
It was described by one research group as a rubble fountain.
A rubble fountain.
It wasn't purely gas creating the elongation, but dust particles being ejected violently due to faster ice sublimation on the sunlit side of the nucleus. Those dust particles initially get ejected preferentially toward the sun.
Until the solar wind pushes them back.
Exactly, until they are quickly overwhelmed by the force of solar radiation pressure, which then pushes them back.
So it was actively spitting rocks at the sun early on, showing off how volatile its surface was. But then as it got closer, solar radiation took over, the reddish color shifted closer to the standard solar color, and a proper tail started to form.
Precisely. The crust was blowing off, but then the classic cometary mechanics took hold. But the true scientific marvel here is the chemistry hidden inside this rock.
Specifically the CO2 overload.
Yeah.
This is what blew the scientific models apart.
Yeah, this is the star of the show. Data poured in from both the James Webb Space Telescope and the SPHEREX mission, confirming that 3I Atlas is unbelievably rich in carbon dioxide, CO2.
Unbelievably rich feels like an understatement. Our reading shows the carbon dioxide to water mixing ratio is incredibly high, about 8.0:1.0.
An 8-to-1 ratio of fizz to water, that is truly baffling if you compare it to anything we find in our own solar system.
It's a massive outlier. Most comets from our Oort cloud or Kuiper belt are primarily water ice. When they start heating up, the main thing they release is water vapor.
Right. But this comet is like opening a warm ancient soda. It's mostly just fizz and pressure. It was active and bright when it was 6.4 AU from the sun, way too far for water ice to be easily sublimating. That early activity must have been driven entirely by the highly volatile CO2.
So why? Why does it have this immense CO2 dominance and comparatively little water vapor observed by JWST? This goes back to its age and origin, right?
It does. There are two main intertwined hypotheses that connect directly to its presumed thick disk origin.
Okay, what's the first one?
First, the CO2 frost line. In any star system, there is a boundary far out where the temperature is cold enough for CO2 to condense into solid ice. This is much farther out than the water ice line.
Ah.
The high CO2 content suggests 3I-8 formed extremely far from its parent star in the bitter cold outer reaches of an ancient protoplanetary disk.
So if it formed further out, that would mean it incorporated more of these highly volatile ices like CO2 and carbon monoxide, right?
Absolutely. And the second hypothesis addresses why we aren't seeing the water that must be there.
Okay.
It suggests 3I-8 has an unusually thick insulating crust, possibly that Tholen-rich space sludge we talked about. This crust is limiting the sublimation of the water ice underneath, effectively trapping the water, while the much more volatile CO2 manages to find cracks and fissures to escape first.
It's like a pressure cooker with a slow leak.
A perfect analogy. The CO2 emissions were calculated at about 129 kilograms per second.
That's almost 300 pounds of pure cosmic fizz streaming off every second.
And compare that to the measured water emission rate, only about 6.6 kilograms per second. That massive disparity suggests either formation in a wildly different environment or incredibly efficient physical isolation of the water core by this ancient, tough crust.
So the CO2 ratio shatters the mold. But the composition puzzle gets even weirder when you look at the heavy metals. This is the moment where astronomers scratch their heads and go, wait, where's the iron?
Right. Telescopes like the Very Large Telescope, the VLT, detected some classic cometary components, cyanide gas and atomic nickel vapor.
Which is normal.
That detection of nickel was actually a great sign for the natural object camp comets emit these metals when silicates are vaporized by the sun.
But here's the quirk, the cosmic aha moment that still requires a new physical explanation. No iron vapor was detected.
This is genuinely odd. In nearly every known solar system comet that exhibits heavy metal outgassing, nickel and iron are typically found together in roughly equal amounts. They vaporize at similar temperatures.
So they should show up together.
They should. The fact that the VLT detected nickel emission first, followed by cyanide and zero iron, is a major cosmic anomaly.
So why would the iron be missing? It's usually the most common heavy metal. Did it simply form from material that was iron depleted?
That's the key question. If it's iron depleted, it suggests formation in a fundamentally different chemical environment than our solar system. Perhaps the parent star's protoplanetary disk had very low metallicity.
Which lines up perfectly with the thick disk theory, since those stars are notoriously metal poor.
Exactly. Or perhaps the iron is sequestered in a chemical form, like magnetite, that requires higher temperatures to vaporize than the nickel did. Either way, this missing iron suggests this piece of rock is a relic of star formation chemistry we simply don't have good models for yet.
Plus, our reading shows it's highly depleted in carbon chain compounds, making it one of the most carbon chain depleted comets ever known. So it's fizzing out CO2 like a warm soda, chemically unbalanced in its heavy metal ratios, and missing complex carbon chains.
Yeah.
It's truly a chaotic, ancient oddball.
And this strange cocktail of blistering velocity, extreme age, and bizarre chemistry is exactly what provided the initial explosive fuel for the speculation that the comet wasn't a comet at all.
And that's where we get into the realm of flying saucers. What do you think? Given the facts, the extreme age, and the bizarre chemistry, does that make the natural explanation sound more outlandish than the sci-fi explanation? Let us know in the comments below.
Now we enter the high drama zone.
My favorite zone. The fact that 3I Atlas possessed such anomalous characteristics fueled one of the most high-profile scientific speculations in recent memory.
The speculation was intense, primarily due to the trajectory. The leading hypothesis, put forward by experts including Avi Loeb and the iForest team, suggested that 3I Atlas could be a piece of extraterrestrial technology. A stealth probe, maybe.
And this wasn't just vague conjecture, right? They focused hard on the geometry of its entry into our system.
Exactly. One major element of this speculation centered on the statistical improbability of its orbital path. Think about interstellar objects. They should, statistically, come screaming into our solar system from random directions.
Right, from all over the place.
Which means their orbital inclination, the angle relative to the plane of our solar system, should be nearly random.
But 3I Atlas was almost flat, wasn't it?
Precisely. Its orbital inclination was only 5 degrees. That means it was nearly aligned with the ecliptic, the plane where all our planets orbit. For an object arriving randomly from deep space, that's a massive coincidence.
It's like throwing a dart from miles away and having it hit exactly parallel to the dartboard.
It is. And the researchers quantified this improbability. The calculation presented in their paper was startling. The likelihood of all 3 inner planets, Venus, Mars, and Jupiter, aligning with 3I Atlas's path by random chance is calculated to be less than 0.005%.
0.005%, that's tiny.
It's tiny. This led them to seriously suggest that such a highly aligned orbit could be intentional, or at least optimally positioned for some kind of observation or maneuver.
So if the alignment was intentional, what was the motive? The theory wasn't just that it was aligned. It suggested the timing of its passage was suspicious, supporting the idea of a clandestine maneuver.
They focused on its perihelion, its closest approach to the Sun, on October 29, 2025. During this time, the comet was totally obscured from Earth by the Sun.
Solar conjunction. A perfect blackout window, astronomically speaking.
And this is where the physics gets really cool and makes the sci-fi hypothesis so compelling. They suggested that this occultation could allow the object to perform an optimal, high-thrust, reverse solar Oberth maneuver.
Okay, let's slow down and define the Oberth maneuver, because that sounds like something straight out of The Expanse.
The Oberth effect, or maneuver, is an aerospace concept where a rocket engine is fired when the spacecraft is moving at its maximum speed, usually near a massive body like the Sun. Because kinetic energy is proportional to the square of velocity, applying thrust at high speed results in a much larger increase in total energy than applying the same thrust when moving slowly.
So you get the biggest boost when you're moving fastest. It's economically efficient for space travel.
Exactly. Now, a reverse solar Oberth maneuver means applying maximum braking thrust at maximum speed near perihelion.
So it's the brakes.
It's hitting the brakes as hard as possible. This would provide the maximum possible deceleration. The theory proposed that 3I Atlas, if artificial, could have used this blackout window to maximize braking thrust to stay bound to the Sun's gravity, all completely undetected by Earth observers.
So a covert braking operation using maximum solar assistance to set up camp in our system. That's genius from a physics standpoint and terrifying from a sci-fi standpoint.
And it creates a brilliant narrative. The paper even explored potential alternative targets if it were intelligently controlled.
Like what?
Calculations showed that if it applied a non-gravitational acceleration component An intercept of Earth was dynamically possible around late November or early December 2025.
Ooh.
Or the same acceleration could signal an intent to rendezvous with Jupiter in March 2026, where it could maximize another O-Birth effect by slowing down into Jupiter's orbit.
That is incredible high-stakes storytelling. An ancient, intelligently controlled probe using a gravity well to secretly slow down and set up an Earth intercept or a Jupiter rendezvous. It absolutely captures the imagination.
It does. And the authors were clear that this was an interesting exercise in its own right and is fun to explore, but science demands verification, and the scientific community pushed back hard, deploying global resources to figure out what this thing really was.
And thankfully, recent data provided overwhelming evidence confirming its natural origin. The biggest piece of evidence didn't come from an optical telescope, but a massive radio telescope looking for signs of life.
It came from the Meerkat radio telescope in South Africa. The proponents of the alien hypothesis were expecting, artificial signals, but the analysis showed the emissions were entirely natural.
And what were they detecting?
Hydroxyl radicals, OH molecules.
That's the smoking gun.
This is the smoking gun. These molecules are the signature byproduct of solar radiation breaking down water vapor released by a comet. When sunlight hits water vapor, H2O, it splits it into hydrogen and hydroxyl. This process fully explained the radio signal, definitively reinforcing its cometary origin.
You just don't get massive natural OH radical emissions from a silent, inert piece of technology.
You don't. So the very radio telescopes meant to detect alien chatter ended up confirming the object was just a really fast, ancient chunk of dirty ice.
And this natural process was vividly confirmed by NASA researchers in October, right?
Yes, who observed intense water jets erupting from the comet nucleus, likening the sheer force of the outburst to a fire hose.
That fire hose analogy immediately makes the alien tech theory a lot less appealing. Instead of a cloaked battleship, it's just a gigantic, ancient piece of volatile ice rapidly melting under the solar glare.
And that overwhelming consensus, supported by all the chemical data from JWST and VLT confirming the CO2, the water, the cyanide, the nickel, it all reaffirms that 3I Atlas is a very weird but ultimately natural comet.
So no alien death probes, just a fascinating, fast-moving, fizzy rock. It's still one heck of a story.
And the speculation drove a massive global effort to collect data while we had the chance.
Indeed it did. Which brings us to its grand tour. Let's track the remainder of its journey and assure everyone listening that this thing posed zero threat to Earth. We need to calm any lingering cosmic nerves we might have stirred up.
Absolutely. 3A Atlas came closest to the Sun on October 29, 2025, at a distance of 1.36 AU.
Which is safely between the orbits of Earth and Mars.
Exactly. It was never coming close to us, even during its occultation.
And its closest flyby of Earth is coming up soon, on December 19th, 2025.
Yes, but at a very safe distance of 1.8 AU. That's about 170 million miles, almost twice the distance between Earth and the Sun.
Okay, so it's truly a safe passage.
After that, it's heading back out into the galaxy from whence it came, never to return.
This rarity, only the third confirmed one we've ever seen, and the fastest spurred an international scramble to capture data while it was here. Because it's a faint object, never visible to the naked eye.
Right, it's currently around magnitude 10.
The heavy lifting had to be done by professional observatories.
This is a rapid, intense, collaborative effort. The closest approaches it made to other planets provided unique observational windows that astronomers just couldn't miss. For example, its close approach to Mars on October 3, 2025 was incredibly valuable.
And we had assets there ready to observe, which is a huge benefit of having a multi-planet space program.
We did. ESA's Trace Gas Orbiter and even China's Tianwen-1 orbiter successfully captured images of the comet during that Mars flyby. This highlights the global urgency. Everyone knew this was a one-time opportunity to sample an object that's potentially 14 billion years old.
You get one shot before it disappears forever.
One shot.
So we also tried to use deep space missions already on assignment, which must have been a scheduling nightmare.
It was a serious use of limited resources. Take the Juno spacecraft, which is currently orbiting Jupiter. It might observe the comet when 3I Atlas passes close to Jupiter on March 16th, 2026.
But Juno's not really built for that, is it?
No, it's optimized for magnetic fields and Jupiter's polar regions. Its cameras have very limited power budgets and pointing capabilities. Using Juno means momentarily interrupting its primary Jupiter science, so it's a high-stakes trade-off.
And what about the JUICE mission, the Jupiter Icy Moons Explorer?
JUICE also attempted observations of the outbound comet in November 2025. The challenge there was completely different and, frankly, fascinating.
Oh.
JUICE was in the inner solar system transiting, and to protect its delicate instruments from the excessive solar heat, it uses its high-gain antenna as a heat shield.
So the antenna is a giant sun umbrella.
It is. But if the antenna is shielding the spacecraft, it can't transmit data back to Earth efficiently. So JUICE had to store any images it took of 3I Atlas.
So we don't have that data yet.
That data won't reach Earth until early 2026, when it gets far enough from the sun to safely reorient and transmit. That level of dedication shutting down communications just to keep the instruments cool enough to snap a picture shows how critical this data is.
That's the true story of this scramble. The incredible scientific effort required to capture this fleeting moment. Every spectrum, every image helps us understand planet formation around other older stars.
And as it leaves, its physical appearance evolved dramatically. It transitioned from that weird, sun-facing rubble fountain early on to a classic comet.
Right, by mid-September, it finally developed a clear anti-solar tail pointing away from the sun, which grew to about 100,000 kilometers long.
It's a spectacular sight, even if we need massive telescopes to see it. The nucleus itself is tiny and highly uncertain because of the huge, bright coma. It's likely less than a kilometer in diameter, similar to 2I Borisov.
What do you think? Which piece of observational data is the most crucial for you? The weird CO2 ratio or the definitive OH radical detection? Drop a comment below. We love hearing what you find most compelling.
Ultimately, 3I-80LS provided an astonishing rapid-fire opportunity to study an object that may predate our solar system by billions of years. It offers unique insights into planetary disk chemistry around ancient stars. Its CO2-rich composition suggests it formed far out, beyond the CO2 frost line, in an environment drastically different from what we typically sample with our native comets.
This deep dive truly reveals that sometimes the natural universe and its raw complexity and age is far stranger and arguably more interesting than the wildest speculations of alien technology.
I think so.
Think about that for a second.
Yeah.
A piece of ice older than our sun, moving faster than any other visitor we've confirmed, spraying nickel and fizzy gas across the galaxy. That's a mind-blowing realization about the history of the Milky Way.
It's proof that there are fundamental, unique chemical differences in planet-building material across the galaxy that we're only just beginning to grasp, and that every new interstellar visitor we find will break another one of our established assumptions.
Before we send you off to mull over the implications of 14-billion-year-old space dirt, we have to throw out a massive thank you for tuning in. We are a small channel, and we would love you on board, so please like and subscribe to our YouTube channel if you want to keep diving deep with us into the universe's biggest puzzles.
And here is the final provocative thought to send you off before you drift off to sleep. The discovery of 3A Atlas was difficult precisely because it originated from the southern celestial hemisphere, coming from the direction of the galactic center, a densely cluttered region of the sky.
Right.
If there are other potentially more common interstellar objects that are coming from directions we are not yet optimized to look at, how many other ancient high-speed visitors are we missing right now, silently ripping through the edge of our detection capabilities?